Thank you everyone for joining at lunchtime. So hopefully you find this interesting. My name is Diego Padilla-Philipps. I am a director in the London Structures team for WSP. I am a structural engineer. Um, my career in the UK has seen me design some really cool projects, including the second tallest building in the UK and in Europe. That's that tall one on the left, 22 Bishopsgate. I've worked with really interesting architects. I'm currently working on the project at the top right, which is the UK Holocaust Memorial Centre, right next to the Houses of Parliament. You can see there, top right. Um, I've worked with artists and sculptures, as you can see on the bottom left, some interesting weird structures, some tall buildings in the Middle East as well, some futuristic projects in Scandinavia, and one of the most challenging projects, it's this one here, which is a tree. We were asked to look at how to replace those props. This tree is 700 years old, and we had to find a way. It was starting to collapse. These props were bent, and then we had to find a way to replace those props. It was possibly the most challenging project I've worked on, even though it was tiny. Um, in 2019, WSP, the company I worked for, um, wanted to do more in reducing the environmental impact of what we do. And when we thought about the 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 carbon emissions from our offices, the buildings that we work in, our offices, our transportation, all of that, in the UK, it added up to something like 20,000 tons of CO2 every year. And it sounds like a lot, 20,000 tons. If it's 10,000 people in the country, it's around 2 tons per person. When you think about the average carbon emissions footprint from a UK person, that's around 10 tons. So that's 2 tons of that is work. That's 20% of what we do. So it sounds like a lot, but then you realize that the emissions from the buildings that we design for our clients, the number is 15 million tons. So it's, 1,000 times greater than anything that we can do as individuals. So we thought we have to reduce the environmental impact of those projects, of the structures that we design for our clients. How do we achieve that? And when they asked me, do you want to help? And well, I didn't really have a choice. And it's been and it's been the driver for my career for the last 5 years. So now I work on supporting every project across the country. We have around 500 projects every year, and I help all of them to reduce the carbon emissions from their designs. And one of the things that we created was a tool that I'll show you in a moment, and then it completely changed everything because it made us realize that how we did things was, stuck in the past. So then now my current role is about not only embedding sustainability into all of our projects, but also looking at how can we automate and bring AI into what we do. So today's talk is about whole building performance. And I know you're structural engineers like me, so you'll be surprised to see that none of the examples in today's presentation have anything to do with structures. And but bear with me, and there's a reason for that. The reason for that is when we dis when we created this product and this process, we had to do it, we had to find funding for it. And what clients needed wasn't structural optimization just yet. It was energy optimization. It was facade performance optimization. And us being a multidisciplinary firm, we have expertise in all of those. So the tool that my team is a structures team, the tool that my team ended up creating actually was a multidisciplinary tool. But the importance is that the principle behind that tool is applicable to everything we do. So you'll see some case studies, some short, brief examples, and the variables that you'll see have nothing to do with structures. One is overheating potential. The other one is facade embodied carbon. The other one is daylight autonomy. But the essence of the talk today is about multi-objective optimization. And when you think about optimization and you think about any project, every project in at work, in life, it's a multi-objective optimization projects. When I give this talk to my colleagues in the UK as well, I say, look, you might not see a beam there, but if your project is just one beam, even if your whole project is designing one beam, that's still a multi-objective optimization project because you have many variables, length, depth, limit depth, openings for services, materials, is it concrete, is it steel, etc. All of these variables, different loadings, different vibration criteria. And at the same time, you have different performance that you have to meet, deflections, stresses, vibration, response factor, etc. So even if the project is one beam, it's a multi-objective optimization problem. So I would like you to keep an open mind for the rest of the talk and see how you can apply the same principles to any project that you're focusing on right now. I mean, even if it's a personal project, even choosing a restaurant to go for dinner is a multi-objective optimization project, I always say. Um, Currently, the paradigm of design is how do we address these three variables, time, cost, and quality? And there's a famous saying that you can't have the three of them, that you need to compromise, so you can only have two of them. Um, well, I want to make this even more challenging. In the current context, we actually have to think about many other variables, performance objectives such as embodied carbon, operational carbon, daylight, energy, etc. So our designs are no longer limited to how much they cost, how long they take, and the quality to achieve them. All of these other variables are coming to us as well, and the performance is expected in all of those aspects. And when you think even more holistically about where these buildings are located, then there's other variables such as circular economy. How do you reuse existing materials? How you generate energy, etc. All of this is just acting simultaneously, and they're all interconnected in a way that it wasn't before, in a way that we didn't care too much about before, but in a way that our clients now expect that to happen. So the challenge is that every discipline is interconnected. I'm going to pause this for a moment because this is what started the whole thing. It's a video that shows a simulation. Um, if you were to, so we had a challenge. The challenge was let's create an algorithm to optimize a building. And on the right hand side, embodied carbon is basically structure, amount of concrete. On the left hand side is daylight, which is architecture. How do you achieve the best amount of daylight into this office floor plan? And the central one is operational carbon, which is energy, which is building services. So the three main disciplines in building design, structures, architecture, and building services. If we have the same area to achieve in this building, and then you ask them in isolation, optimize for the best daylight, the best energy performance, and the least amount of concrete. Now think about what type of building are you going to get if you had no constraints in terms of volume, size, etc. You only have to hit the same area. So I'm going to guess, because we're all structural engineers, that we're thinking, right, low embodied carbon, like least amount of concrete, it cannot be a tower. It has to be low rise, it has to be flat, it has to be shallow foundations. We can tell. And architecture could also be a bit intuitive. You think, well, maybe if you want daylight, it can't be a massive floor plate. It has to be narrow so that the daylight can access. And because you need a lot of area, it might end up being a tower. So that is a bit intuitive. But for me, building services was a complete surprise. I had no idea what to expect. So we ran this iteration. And then by the end of it, we realized that, yes, on the left, the architecture most efficient solution was a tower. On the right-hand side, the most efficient structural solution was a low-rise building, but then again, that is terrible for daylight and it's bad for building services because you got all the heat loss or heat gains on that roof. And then the mechanical engineer said, well, if you want to optimize this building to gain and lose the least amount of energy, it has to be a basement, buried in the ground. And although it sounds like a joke, um, it makes you realize that buildings, if each of us wants to optimize in isolation, we'll end up with completely different designs. And there's a reason why buildings look the way they do on the left, is because someone comes in first. And it could be the architect that comes in first and says, this is my shape, or it could be the cost consultant or the planning consultant that says, these are my constraints. And what happens is that the following trades, the following engineerings, we're left having to fight against physics, having to fight against even gravity to make those designs work. We're not starting from the most efficient point of view. Look how different are these three designs, constantly pulling in different directions. And the process is currently linear. Architecture comes first, and then they take some advice from facades, and in the end, become MEP, and then structures, and then finally sustainability. But actually, in some cases, it's even more linear than that. And some of the aspects of it, like sustainability, are left until the very, very end. And when you try to optimize something like, let's say, how do I reduce embodied carbon? All of the other aspects of the things that I'm trying to balance at the same time change, and it's not intuitive. So it's not easy just to say, well, if you reduce that energy, then something happens. They're not directly proportional. They're not linear. They are not even in the same order of magnitude in some cases. It's a real struggle to try to optimize for all these variables. So we thought, how can we achieve any building efficiency? And we thought, all right, let's simplify this to a few variables and let's iterate. So we created a little algorithm that was for any given site, it would um, test different shapes, different facade types, um, different window sizes, different orientations of the building with some constraints because this is a real city landscape. And every time we created one of these massings, we would evaluate a parameter. In this case, the parameters were daylight, building embodied carbon, and operational carbon. And we found a way to do a quick simulation. And that's the interesting thing because these simulations, they used to take, hours for each of these dots. So that we compressed that into a simplified approach so that we could test hundreds of different options in in a few hours, overnight. Now it happens in minutes because we've gone into like cloud computing and it's more powerful. But the thing is that now we have all of this information, hundreds of options that describe performance in more than one variable, for more than one variable. And from that, you can choose, you can start looking at these graphs and say, look, if you're here on the left, the closer you are to the origin, that is the most efficient solution. So it's a data-driven, evidence-driven, performance-driven approach to building design. And that's how we can now help our clients drive and achieve their objectives. So what is this co-design framework that I'm talking about? Well, it is about performance and it's about being driven by humans. It's a I need to breathe first. It's a systems level integrative design approach that unites multiple disciplines to collaboratively address the complexity of building performance. In other words, it's multidisciplinary, it's based on data, and it's based on collaboration so that we can unlock not just one discipline, but all of the disciplines together. And it's based on three pillars. First, as we said, being multidisciplinary. The next one is early stage simulation. And the third one is evidence, which is the result from the simulation. And this is the key difference that, uh, well, first, that it enables you to look at all of the disciplines at the same time, or whichever you choose to evaluate, based and under the umbrella of sustainability. But the main difference is this, is that currently the business model for an engineering project means that at the early stages you you don't have enough fees to do any simulations, any analysis. So buildings are typically defined at a concept stage based on intuition, based on experience, because we've done this before, and based on simplifications. And it's just the nature of the business. That is how much we get paid. That is how we do it. There is no opportunity to really bring detailed engineering to an early stage so that we can influence that design. And at an early stage, that's when we can influence the design the most. Sometimes the best thing you can do for a building, for example, a tall building that is subject to strong wind forces, sometimes the best thing you can do is change that shape, smooth the corners, create some small variations in the shape along its height. And you can only do that at an early stage because after you've gone through a planning approval process, the architect or the client, they already like the shape and you can't change it. You see, so the earlier you make those interventions, the more impact they have. Um, but at that stage, no one has a simulation, no one has analysis in some cases. We just go by sketches and assumptions. What this co-design framework tries to achieve is replace that with, not replace, enhance that with simulations, with computer simulations that lead to data, that lead to evidence, because that's when you can make the biggest impact. Some of these variables that we look at, and again, this has very little to do with structures, but if you think about, the envelope, the facade on the left, and the things, the objectives that you have to achieve, such as daylight, glare, solar potential, energy, they are affected by different simulations in the middle. The daylight simulation will give you some of them, but the energy simulation will give you something else. And then how do you find that balance between the results from the different simulations? That is the challenge, and that is what this co-design tries to achieve. And it's trying to embed this into a much bigger sort of paradigm, which is what we call, performance-informed, human-driven, which is how do we embed sustainability? It's through performance and it's through regeneration, regenerative design. And if on top of that we add the enhancements provided by AI, combined with HI, human intelligence, we get what we call performance-informed, human-driven augmented intelligence, which is the direction the industry needs to go. It is about embedding sustainability, creating better buildings using the principles of regenerative design and enhancing our intuition through the insights from artificial intelligence so that we get this augmented intelligence. It's not really replacing humans, it's giving us all the tools to drive improvements and growth and basically create much better buildings, which is in the end what we need as a society. Right, so I'm going to pause it for a second and I'm going to show you some projects, some examples. And again, I want you to bear with me and keep an open mind because you're not going to find columns and beams or slabs or foundations in these examples. The variables that we had to deal with, they responded to what the clients needed. Clients needed daylight, so we responded. So you imagine some structural engineers trying to understand how do you assess daylight? um, how do we create something that enables that sort of understanding? So the first client was but this applies to anything, and hopefully you can see that. This client said, excuse me, the client said, I have this really impossible problem to solve. Help me. I've designed these apartments, and the daylight assessment for my planning application or construction permit, uh, it's telling me that the windows are too small. The apartments need bigger windows. Okay, but when I increase the window size, suddenly there's all this extra heat coming through. So I have to either, then it tells me that the cooling load inside is too high. So I have to introduce air conditioning. And in the UK, as you might know, we're not very good with air conditioning. We haven't got air conditioning in our houses. So adding air conditioning because we don't need it. But an apartment like this overheats even when the temperature outside is 20 degrees, which is most of the year, 20 degrees. And inside is like 27, 28, and it goes even higher than that. So you need um, to cool it down. So to minimize that, they said, I'm going to have to install this film in purple, and it doesn't look good with the building. And I just don't know how to do it. So what we did was we created an analysis model, a parametric model, where every variable of this apartment was a variable, every aspect. And then we evaluated performance for each combination. And it's done using a genetic algorithm so that it doesn't test absolutely every single option. It just learns from each generation of models. And every point, as you can see, every point is on the right-hand side, changing some of those variables, the size of the window, the depth, the thickness of the window, the type of shading. Um, and in the end, after like literally 1,000 different iterations, we said to them, this is what you need to do. You have to reduce the window size. But because we're changing that film to this type of louver, the shading, we're actually increasing the transparency of that. So you're getting the same daylight, even though the window's smaller. And because we're introducing this tiny edge around the window, you're creating shade in those windows, which means that you're getting less direct um, sunlight. So it's direct less heat. So um, you don't have to use air conditioning anymore. Excuse me. And and then the planning consultant, they couldn't accept it because they thought they're making the window smaller. So we used this to justify this as evidence. And it was the first time that someone broke away from the traditional planning process to tell people you can show evidence of these sorts of analysis. And we couldn't do in the past 1,000 analysis because no one has the fees to do 1,000 analysis. But now we can do 1,000 analysis in a few hours. So then this client said, right, well, can I do this for a whole building? So now this is a whole floor of a 30-story building. You can see the apartment layouts inside where they wanted the same. They wanted full windows, looking at the river, etc. And then we just went and tested every single option and created that surface of possibilities. Then that leads to, nearly 2,000 simulations. And this is for me the biggest difference between what we do right now as engineers. Currently, as engineers, we the architect proposes this red dot, and we say, actually, based on my experience, based on my intuition, based on what I know, I propose one, two, or three different options, three of these dots. And they might be, really well thought through because we've got years of experience. But we never have the opportunity to look at the entire design spectrum, which is what this allows us to do. Each of these points is a simulation that has evaluated the four parameters in the x-axis, the y-axis, the z-axis, and the color, which is four parameters that are four performance indicators that have been assessed. So then what we do is we start filtering those values, and we filter in one axis and we filter in the other axis, and then we give the client, these are the options that meet your brief and can achieve what you want, and they are better than anything else we could have started with. And then we give the architect and the client what it means to have different balconies, different window sizes at different sides of the building, and they can choose, mix and match until they achieve that. So then the client said, "Oh, that's brilliant. So can I also look at a tall building?" And then we created a tool, and then this one has a little bit of structural input because he's looking at building embodied carbon as well. So we looked at this tall tower, which is like 40 stories, to see what it could be. So then another client looked at this and said, "All right, but can you help me with more than one building?" And we said, "Yes, of course. What do you need?" And they said, "Look, we can't really make it balance the amount of daylight and the amount of overheating. All of these apartments are overheating. What can I do?" And we asked them, "Well, what can I change? What's the parameter?" And they said, "The only thing you can change is the height of the buildings. You need to keep everything else the same and you need to achieve the same area." So we started playing with buildings, different blocks of different heights. And every time there was one model, and we iterated and we generated a dot along this line so that we could drive performance. And from those, we filtered and then we chose what was something, very similar. It's very similar to the original. But with these small changes, we managed to improve um, the thermal performance of some of those apartments. Um, but at the same time, we reduce the surface of glass, which led to like £500,000 saving. And that wasn't one of the performance things that they wanted to achieve. But when they saw that and they thought, "Well, this is great. So now I have £500,000 less um, to spend on this building." So then the same client said, "Right, then help me even more. Look at what can I do with one of these buildings? And I want to look at every single apartment and I want to understand what are the challenges." So we created clusters of apartments so we could evaluate the same performance for each of those, which then enabled us to tell the client, "Look, the apartments in green, you can improve daylight by doing this. The apartments in yellow, you can do this. And the apartments in red, you have to actually change the layout because currently, these are the lower ground, the ground floor apartments. They only get daylight from one side. So this is a really challenge for you. And if you want to reduce the energy or reduce your heating potential for these apartments, these blue ones here, C1, because they're south facing, you have to change the window sizes, so that you can design out the mechanical cooling. So we can now evaluate every apartment at an early stage to help them drive those decisions. And finally, the last example is what we did for the National Health Service, which they looked at us and said, "Well, how can we bring this into all the hospitals that we're trying to build?" So we said, "Well, what can we do?" And they said, "Look, we currently have 9 designs, 9 possible hospital designs that we want to build across the country." And we realized that this was maybe too late for us to come in. So we said, "Okay, let's look at your designs and help you." And this is the main difference between traditional concept engineering and what we can do now with technology. If you have, say, for example, you take one of these options, option 6 is looks like the best performing in terms of daylight. But obviously, because of that, it is the worst in terms of overheating. So when you look at these designs, you had 9 options. And each option had a different position, this performance graph in X, in Y, and in the color scheme. They perform differently. Nobody has the ability to test everything in between. So using multi-objective optimization tools like these ones, what you can do is create that, complete the surface of performance. And again, this is looking at daylight, overheating, and embodied carbon facade, but it could be any project, any option that we have created for a project, a concept. It's only one option, one of 9, not one of 1,000. And these 1,000 options allow us now to look at the whole design spectrum and think, what does improvement mean? And this is an interesting point because when we look at, say, option 3 on the bottom left, if we were to change, make some small changes, you can barely see the changes between 3 and 3A. Um, that moves as this arrow is doing right now, and it's improving performance drastically. If you look at option 6, just by rotating the massing ever so slightly, it improves performance by bringing the 6 to 6A to the center. And again, the same for option 9. So what we concluded um, uh, from this short assessment was if the NHS wanted to achieve the best balance in performance for these hospitals, they needed to choose hospital type C, but then they needed to make these small changes, basically just rotating the building by 20 degrees and then introducing this connecting link between the three, arms of the building. And with such small change, imagine you're reducing the energy intensity and the energy consumption of a hospital during its whole operation life. It's it's a massive amount of savings in terms of energy, in terms of cost. So just by making that such a small change, that is the value of multi-objective optimization. So then we thought, all right, can we create our own hospitals? If every room is a box in this algorithm, can we start testing them to see what happens to the floor plate as we put one room next to the other? And it became really complex. Hospitals are a lot more complex than this. So we didn't pursue this dream, but it made us realize that this is the future of what we do. It's all about being able to um, to change how we do things so that we use the insights from 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 analysis, from simulation, but now. So currently we follow a design process which is assumptions and intuition and experience that then that leads to and don't get me wrong, some of those assumptions are incredibly valuable and valid, but they constrain the final result. And then we go into detailed design and then we evaluate that. Imagine if we could bring those insights from design to the early stages so that we can make even more better informed decisions. And 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 sometimes what we do is in response to what the architect wanted, and the architect made a decision to have a cantilever or a column or an inclined thing or something without any insights from engineering or from other disciplines. So imagine if we could all have those insights at an early stage. So what we are trying to achieve here is this new design paradigm. So currently, what we do is, we start with a dream, and it could be the architect's dream, it could be the client's dream. It's never the engineer's dream, but it's the dream. And then we spend the entire design process, value engineering on this journey of disappointment until we get what we can pay for. And it's a struggle, and it's not nice. It's every building is just like that. What we're trying to do is flip that upside down. So if we start with a co-design multi-objective optimization approach, you begin with the absolutely most efficient solution for whatever parameters. It could be daylight, it could be embodied carbon, it could be structure, it could be foundation depth, it could be cost. We can all define those variables that matter to us. If we start with those, or the most efficient, then the rest of the design process is an actual opposite journey, of joy. And we add more cost, we add more carbon, we add more, then we make informed decisions to add to it until we get the absolute best product. That is the mindset that we need to change as an industry, from this negative approach to building design to the complete opposite of how do we achieve the best possible product. And the only way, or one of the only ways to achieve that, is to start with the absolutely most efficient and then grow from that. So that was me. And hopefully, although this had very little to do with structures, hopefully you had the opportunity to see how you can apply these principles to anything that you do. Multi-objective optimization is something that is applicable to every aspect of work, of life, and it's becoming easier and easier with automated tools, with the explosion of AI and everything happening around us. It's the way forward, and we have to embrace it. So hopefully this was interesting. Hopefully you saw, hopefully I was able to share these experiences with you, and I look forward to answering any of your thoughts and questions.